Jai Hind everyone. I am Vikas Rathi, working in Ajay Garg Engineering College as an assistant professor. Today, I am discussing about the topic which I am going to discuss is basically Newton's rings and its application. The subject name is Engineering Physics. Subject code is BAS 101. Newton's rings is basically based on interference in thin films. In previous lectures, I have discussed about the thin films. So today I will discuss one of the application of the thin films, which is Newton's rings, and after that I will discuss its applications. So I will discuss Newton's rings and its application today. References for this, they are textbook of Engineering Physics by Navneet Gupta, a textbook of Optics by Ajay Ghatak, Engineering Physics by SK Gupta, Engineering Physics by SL Gupta. So these are the references for this topic. The topic is Newton's rings. Again, the topic is Newton's rings and its applications. So what are Newton's rings? First, I will discuss what are Newton's rings. How Newton's rings are formed basically. Okay. So when a plano-convex lens of large radius of curvature is placed with its convex surface in contact with a plane glass plate, an air film is enclosed between the upper surface of the plate and the lower surface of the lens. If a monochromatic light is allowed to fall normally on this film, then alternate bright and dark concentric rings with dark center are formed, and these rings are known as Newton's rings. So basically, how Newton's rings are formed basically. So if we place a large radius of curvature of plano-convex lens, okay, on a plane glass sheet like this, okay, so then this is the gap between these two surfaces, and air is filled between these two surfaces. That means between this gap, okay. So here the film is formed basically. So thin film is formed between these two surfaces. So this is basically a thin film which is formed between these two surfaces. Okay. So why one question is this: why we take this large radius of curvature of plano-convex lens? Okay. If we take the large radius of curvature of plano-convex lens, then this gap, the gap between these two surfaces, that will be of the order of wavelength of light. Okay, so which is the basic requirement for the thin film formation. So that's why we will take the large radius of curvature of plano-convex lens for the formation of Newton's rings. Now I will discuss experimental setup for this formation of Newton's rings. Here we can see this is the experimental setup for the Newton's rings arrangement. Here we are required a light source, which is a monochromatic light source, and which is here a sodium lamp. Okay. Then plane glass plate P and a plano-convex lens C is required for this. Okay. How the rings are formed basically, how the interference pattern is observed here. So when this light is incident on a glass plate G, and which is put at an angle 45 degree to the incident light. So then light after reflecting from this glass plate will incident on this system, which is formed basically through a plane glass plate and a plano-convex lens. So then what will happen when light is reflected from the lower surface of the film and the upper surface of the film? That means light is reflected basically lower surface of the film means upper surface of the plane glass plate. So that means light will reflect from the lower surface of the film, that is from the upper surface of the plane glass plate, and another ray will reflect from the upper surface of the thin film. That means lower surface of the plano-convex lens. So that means the interference will occur between the rays reflected from the lower and upper surface of the thin film. That means again from the upper surface of the plane glass plate P and the lower surface of the plano-convex lens C here. So then they will get interfere in space, and due to their superposition, due to their interference, we will see a interference pattern which is formed in the form of rings basically, and that interference pattern is observed through the traveling microscope. So this is the basic components which are required for the formation of Newton's rings. So we require a plain glass plate and a plano-convex lens, basically for the formation of thin films, and a light source, okay, through that we can illuminate that system. And to see this interference pattern, we require a system. Basically here this is microscope, and this is basically traveling microscope, and through which we can observe this interference pattern. So in this way we can observe the interference thin films, basically Newton's rings. And this is the picture. This picture shows how the rings will form, how the interference pattern will form in this arrangement. So through this traveling microscope, in the focal plane of the microscope, we will see this type of pattern, which is in the form of rings, basically. So here you can see this is the center of the rings, and we will have then concentric rings of circular form here. Okay, so the center of these rings, that will be dark, and you will see dark and bright concentric rings. So this is the these rings, these concentric rings basically are known as Newton's rings. Now we'll discuss the theory behind it, how these rings are formed due to interference. So there are two systems. We can observe the Newton's rings in two cases. First, I will discuss the reflected system, then I will discuss the transmitted system. So first I will discuss how Newton's rings are formed due to the reflected system. Reflected system means here the rays reflected from the film, that means lower and upper surface of the thin film, basically. So the formation of the Newton's rings, or formation of the interference pattern, basically depends upon the phase difference and path difference between the reflected rays. So that means it will depends upon the what is the phase difference between the reflected rays from the different part of the thin film, or their corresponding path difference. So to discuss the formation of Newton's rings or the theory of the reflected system, first of all we will find out the path difference between the reflected rays from upper and lower surface of the thin film. So here I have shown this part of the arrangement here. Here we will have a glass plate and a plano-convex lens C here, and I have shown here two reflected rays R1 and R2. Basically they are represented by ray 1 and ray 2. Basically this is the incident ray, and these are the R1 and R2. These are the reflected rays reflected from the, one of them is reflected from the point A, which is the upper surface of the film, that means lower surface of the plano-convex lens, and another ray will reflect it, it will refract and then reflect, and it will go through this path, that means in the form of ray 2. So it will go like this, and it will reflect it, basically refracted and reflected from the lower surface of the film, that means upper surface of the plain glass plate. And these two rays, ray 1 and ray 2, they will get interfere in space, and due to their interference, okay, we will see basically the Newton's rings, interference Newton's rings. So first of all we will discuss what is the path difference between ray 1 and 2. So basically thin film, they are divided into two categories. One of them is uniform thickness thin film, and another one is wedge-shaped film, varying thickness thin film. Basically this is the second case. Newton's rings are basically the second case of the thin film. That means the form of the film, air film, is basically varying thickness. The thickness of the film at the point of contact, oh, this is minimum, almost zero, and now it is gradually increasing. If we go away, then the thickness of the film, air film, is gradually increasing in outside. Okay, so this is the varying thickness thin film, basically. So this is also known as wedge-shaped film. And the theory of this wedge-shaped film we have discussed already. So I will use here directly what will be the path difference between the ray 1 and 2. So I will write here a direct path difference between ray 1 and 2. Then according to Newton's rings, we will with some constraints, with some conditions, we will finally find out the what is the path difference between the ray 1 and 2 in our case, in case of Newton's rings. So I will write first, I will write here, okay, a general formula for the wedge-shaped thin film. So here this the path difference between ray 1 and 2, that will be 2 mu t cos r plus theta plus minus lambda by 2. So here r, this small r, this is the angle of refraction. Okay, theta is the angle of the film, that means angle between the two surfaces. Lambda is the light wavelength of the incident light source. T is the thickness at the point of incidence. Okay, and mu is the refractive index of the film. Now, for our case, because the film is formed in air, so for the air film, we will take here the refractive index of the film 1. That means here we will put mu equal to 1, because in our case, the film is formed in air. So for air, the refractive index of the air is 1. So that means we will take here mu equal to 1. So then in Newton's rings experiment, basically the lights are normal incidence. Lights are normal incidence. So that's why for normal incidence, basically the angle of incidence and angle of refraction, they will be 0. So that means in our case, in case of Newton's rings, light is normal incidence on the system. That means on the plane glass plate and the plano-convex lens. That's why we will take here I and R, they will be 0 here. So if for air film, mu will be equal to 1, and for the normal incidence, angle of refraction will be 0. So then the value of cos r plus theta, that will be equal to 1 here. Basically, if you put r equal to 0, and then it will be equal to, basically this will now becomes, if you put r equal to 0, so cos theta. Okay, so cos theta, if theta is very small, so for a small value of theta, cos theta tends to 1. So that's why this factor cos r plus theta tends to 1 basically here in equation 1. Okay, mu will be 1. So finally the part difference will be 2t plus minus lambda by 2. Okay, the role of this factor, basically now I want to discuss why we put this factor here in case of Newton's rings plus minus lambda by 2 for this part difference in equation 1. So this is basically according to the Stokes law. In optics, if a light ray is reflected from the denser medium, then there will be a extra phase difference of pi or corresponding part difference of lambda by 2. So here we will see that this ray from point, this lower surface of the film, that means from the glass surface, the ray is reflected, ray 2 is reflected from the lower surface of the film, and lower surface of the film is plain glass plate, and which is basically the denser medium. Okay, so that means light from point A, which is going towards this glass plate G, it is coming from the rare medium and going towards the denser medium. So that means ray 2 is reflected from the denser medium 1 times. That's why according to Stokes law, this ray will have a extra phase difference of pi and the corresponding part difference of lambda by 2. That means we have to put here for this factor plus minus lambda by 2 here. So according to Stokes law, again I will repeat, according to Stokes law, if a light ray is reflected from the denser medium, then there will be a extra phase difference of pi or corresponding part difference of lambda by 2. So that's why we have put this factor here. Okay, so that means finally the part difference in our case will be 2t plus minus lambda by 2. Now the pattern is formed in the form of dark and bright rings. So first we will put here, we will apply the condition of constructive and destructive interference. That means for bright and dark rings, if the part difference equal to integer multiple of lambda, then we will have a constructive interference. That means there will be a maximum intensity, and we will have that pattern, that ring, bright ring basically. So that means for bright ring, there will be a condition. That means if this part difference means 2t plus minus lambda by 2 equal to n lambda, then we will have bright rings. Okay, that means if this condition is satisfied, then we will have bright rings there. So that means condition for bright rings, for bright ring, we will put that part difference 2t plus minus lambda by 2 equal to n lambda, and we will have that finally we will have this condition 2t equal to 2n plus minus 1 into lambda by 2. Now if we put, we can take here plus sign or minus sign. So for example, if you take plus sign, okay, then we will start n from 0. Okay, now we can take here minus sign also. If we put here in this equation minus sign, then we will have to start n from 1. right? So we will take here plus sign or minus sign, but according to that we have to select the value of n, this integer. Okay, 0 for plus and for minus sign it is 1. Now condition for dark rings. Now if we put this power difference equal to odd multiple of lambda by 2, then we will have a destructive interference. So that means for dark rings, this power difference must be equal to odd multiple of lambda by 2. That means 2t plus minus lambda by 2 must be equal to 2n plus minus 1 into lambda by 2. And if we simplify this equation, then we will have condition for the dark rings 2t equal to n lambda. And here we will start this value of n from 0. Okay. So, and maybe 0, 1, 2, 3 and so on. So, equation 3 and 4, these equations represents condition for the bright and dark rings. Okay. So, here one point we can discuss at the point of contact. Okay. At the point of contact, means where this plano convex lens and the glass plate in contact. So, there the thickness of the film is 0. That means we can put there t equal to 0. And if we put in power difference t equal to 0, then we will have power difference only plus minus lambda by 2 or lambda by 2. And this is the condition for the destructive interference. This is the condition for the minima. That means the center of the rings in case of the reflected system, that will be always dark. It will remains dark basically. Okay. Another thing. Now the fringes, they are formed in the form of circle because it will basically depends upon the power difference, and the power difference depends upon the thickness of the film t and the wavelength of the light source. The wavelength of the light source is basically remains same. Lambda is remains same there. T is varying. So that means the formation of rings, that will depends upon the thickness of the film. Thickness is varying basically, but it will remain say the ear film is have a symmetry about the point of contact. That means at a particular distance from the point of contact, the thickness of the film remains same, and the locus of points, that will represent basically a circle. So that means there at that circle, if there will be a condition of destructive interference or constructive interference, okay, then we will have dark ring or bright ring, depends upon that. So that means the formation of rings, that will depends on the power difference, and power difference basically depends upon this factor t, which represents thickness of the film, and thickness of the film remains same at the equal distance from the point of contact, and which will represent the points of the locus of points represent basically a circle. So that's why the pattern that will be seen in the form of rings basically. Now for further discuss, now we will find out diameters of dark and bright rings, and to find out the diameter of dark and bright rings, we will complete this geometry. Here we can see this diagram. So according to that diagram, we can find out the diameters of the different dark and bright rings basically. So here we will use this geometrical property of the circle basically. Okay, this is this circle. Okay, here this AOB, this is the plano-convex lens, and this lower part is a glass plate, and if the radius of curvature of the plano-convex lens is r, so that means this CB, this distance will be equal to the radius of curvature of the plano-convex lens. So capital R is here. Suppose the radius of curvature of a plano-convex lens, so then this CB distance will be equal to capital R. Also this CO distance, that will be equal to the radius of curvature of the plano-convex lens. So this is also equal to capital R. Now we will take this property here, AD into dB, AD into dB. Okay, AD into dB, this will be equal to OD. OD means this distance into DE. DE means this. DE point represents basically here, this is CD, and DE is point basically. DE is basically here. Okay, so we'll put here this point. This is basically here. Okay. So this AD equal to R, AD and DB, they equal to R, and if we simplify this, OD will take commons, and then it will be equal to 2R minus OD. Okay, or we can take this property, we can find out the relation between thickness of the film and the radius of the rings. According to this diagram, we can put here this distance CD. CD will be equal to basically R minus T. Okay, if this distance is T here, and then it will be equal to R minus T. So in this right angle triangle, CEB, this CB square will be equal to BE square plus CE square. So by using this property of this right angle triangle, so R square will be equal to, if this distance is R, so this will be equal to R square plus CD, and CD will be R minus T whole square. Now if you simplify this, R square equal to small r square plus capital R square plus T square minus twice RT. So this R square cancel, and here we will have that this small r square will be equal to twice RT minus T square. Now we can neglect this term here, T square, because this is the thickness of the film, and the thickness of the film is very small, and radius of curvature of lens is very large. So with respect to this 2RT factor, we can neglect this T square factor. So with this relation, okay, we will find again this condition. So R square will be equal to twice RT. So by using this relation, we can have the relation between thickness of the film and the radius of the rings. So to find out the diameter of the rings, we will use this relation between thickness of the film T and the radius of the rings small r. So first of all, if you want to find out the diameters of bright rings, so first we will put this condition 2T, which is the condition for the bright ring, formation of the bright rings, 2T equal to 2n plus minus 1 into lambda by 2. And here R square will be equal to, if we take this plus sign, then it will be equal to 2n plus 1 into lambda by 2. And now we will put this R in this thickness here. Basically what we did here, R, T is replaced with R square by twice R. Okay, so in this equation, if we replace this T with R square by twice R, and if we simplify that, then we will have this radius of the nth bright ring. So Rn represents radius of the nth bright ring. So expressions for the nth bright ring, that will be root of 2n plus 1 into lambda r by 2. And here this lambda r2, these are constants basically. So that means diameter. If you find out the diameter, so then if dn is the diameter of nth dark ring, so it will be twice of radius of that particular ring. So diameter of nth dark ring will be equal to root 2 into 2n plus 1 into lambda r basically. Or that means dn is proportional to root 2n plus 1. Now we can see here that if we put here n equal to 0, 1, 2, 3 and so on, then diameter, that will be proportional to this will be proportional to, if you put here n equal to 0, it will be proportional to root 1. Then for n equal to 1, it will be root 3, proportional to root 3. Similarly root 5 and so on. That means the diameters of bright rings that are proportional to the root of odd natural numbers basically. Similarly, we can find out the diameters of dark rings, and we have already find out this condition for the dark ring, 2t equal to n lambda. And to find out the again the radius or diameter of the dark rings, we will use that condition which was here this t equal to r and or r square by twice r. In this equation, we will replace t with r square upon twice r. We are now this r, small r, will represent radius of the nth dark ring. So that means expressions for the nth dark ring means Rn, that will be root small n lambda r here. Now to find out the diameter again, what we will do? We will put, if we consider that dn, capital Dn represents diameter of nth dark ring, that means here we will put Rn with dn by 2. Then we will have this relation here, dn equal to root 4n lambda r. This lambda and r, these are constants. 4 is also a constant. So dn, that means diameter of nth dark ring, will be proportional to root n. So now if we put n, we cannot take here n equal to 0 because diameter cannot be 0 of any ring. So n cannot be 0. So n will start from 1, 2 and so on. So if you put n equal to 1, so then it will be proportional to root 1, root 2, root 3, and so on. That means the diameter of dark rings are proportional to roots of natural numbers. Okay, so in this way we can find out that diameter of bright and dark rings, that will depends upon which factors, okay, how it will vary. Okay, this is the second case, transmitted system, theory of the transmitted system. Till now we have discussed theory of reflected system. That means how the rings are formed in the reflected system. Okay, so what will be the condition for the dark ring, for the bright rings in case of the reflected system? Similarly, we can discuss formation of Newton's rings in transmitted system. Means how the transmitted rays will be transmitted from the thin film. So this is the ray diagram here. This is the ray diagram. Okay, here you can see these R1 and R2, these are the reflected rays here, and T1 and T2, these are the transmitted rays. So to how the rings are formed in case of the transmitted system, first of all we have to find out the path difference between the transmitted rays T1 and T2. Now again we can see this is the vitiate film, non-uniform thickness thin film. So here we will again apply the theory of the vitiate film, and already we have find out that path difference between the transmitted rays in case of the non-uniform thickness thin film, vitiate film, and that was 2 mu t cos r plus theta, and there will be no extra phase difference or path difference of phi or plus minus lambda by 2 factor. Okay, we have not considered this factor here. Okay, so this is the important discussion here. Okay, you can see light is coming this way here. So first ray will reflect from this reflected ray R1, then it will refract here, then it will transmit it. Then at this point, lower point, suppose this is point A, from point A it is reflected from this point A, that will, then it will go through this path, then it will reflect from, suppose this is point B, from point B here, then it will reflect and it will come in the form of T2 transmitted rays. So that means before coming out this transmitted ray T2, it is reflected 2 times from the denser medium. That means from point A, this is basically a glass plate which is denser medium. So it will reflect from point A, that means from the denser medium, then it will reflect from point B, again from the denser medium. That means before it will get out from the thin film, that means this T2 ray, when it will come, so it will reflect 2 times from the denser medium, that means from point A and B. So according to Stokes law, there will be a phase change of pi or corresponding path difference of plus minus lambda by 2. So that means there will be a extra path difference of plus minus lambda by 2, plus minus lambda by 2, and which will be equal to plus minus lambda basically. And this plus minus lambda factor, it will not change the condition of dark and bright rings. That means if dark ring is formed there, then it will remain dark, and if bright ring is formed there, then they will remain bright, because it will not affect the condition of path difference. For example, for the constructive interference, path difference between the reflected rays or transmitted rays, that should be equal to 0, lambda, 2 lambda, and so on. Then if we add this plus minus lambda by 2 factor in 0, in lambda, in 2 lambda, then it will remains condition for the constructive interference. So it will, this factor plus minus lambda, it will not change the condition of the path difference. That means if there will be a constructive interference, it will remain constructive, and if there is a destructive interference, then it will remain destructive interference. So we cannot add this factor plus minus lambda by 2 here. Okay, so we can take only this part difference 2 mu t cos r plus theta. Okay, so again we will have that the film is formed in air, so again we will take mu equal to 1. Then again light is incidence normally on the system, that means on the plano-convex lens and the glass plate, that means on the thin film. So I and R, they will be 0 again. Now if we put R equal to 0, then cos theta, okay, it will be equal to cos theta, and if theta is small, then cos theta tends to 1. Okay, so part difference will be only 2t here. Okay, so now at center we can discuss here what will happen at center. At center thickness of the film is 0, so part difference will be 0, and part difference 0, lambda 2 lambda represents conditions for the constructive interference, so that's why center of the rings in case of the transmitted system will be bright. In case of reflected system it will be dark, but in case of transmitted system it will be bright. Again, similarly we can find out the condition for bright and dark rings. So for bright rings we will put part difference this delta equal to n lambda. Okay, so now this is the condition for the bright rings, 2t equal to n lambda. It was in reflected system it was condition for the dark ring. Okay, and this now here for the dark rings, part difference that should be equal to odd multiple of lambda by 2. Now part difference is 2t, so here equation 4 represents condition for the dark rings. Okay, so again we have already discussed, if we take here plus sign, then n will start from 0, and if you take here minus sign, then n will start from 1, and so on. Similarly we can find out the diameters of the dark and bright rings in case of the transmitted system. So again we will use this condition which we have already used in reflected system, relation between thickness of the film and the radius of the rings, that means t equal to r square by twice r. Okay, so to find out the condition for the bright rings, okay, we will have this condition for the bright rings. Okay, 2t equal to n lambda, and here we will put t will replace in equation 3 with r square by twice r. So with this factor, if Rn here represents a radius of the nth bright ring, then Rn will be equal to this root n lambda r here. Then if we replace this with diameter of the nth bright ring, so then we will have a relation for this diameter of nth dark bright ring, dn equal to root 4n lambda r, and which was basically condition or diameter for the dark rings in case of reflected system. Okay, so here the diameters of the rings will be proportional to root of n. That means you can say diameters of bright rings are proportional to roots of natural numbers. Similarly, we can find out the diameters of dark rings. So for diameters of dark rings, this is the condition 2t equal to 2n plus minus 1 into lambda by 2, condition for the dark rings. Here again we will replace this t with r square upon twice r. Okay, if we replace this, then we will have r square equal to 2n plus 1 into lambda r by 2. If we take plus sign, similarly we can find out the diameter of nth dark ring. Okay, so for diameter we will replace this Rn with dn by 2, if dn represents diameter of nth dark ring. So then this will be proportional to root 2n plus 1 here. So that means diameters of dark rings will be proportional to roots of odd natural numbers. Okay, so this is the theory explanation about the formation of Newton's rings in case of reflected and transmitted system. Okay, so in next lecture we will discuss applications of Newton's rings. There are two applications of Newton's rings: determination of wavelength of the sodium light and refractive index of a transparent liquid. Okay, so in next lecture we will discuss these two applications of the Newton's laws. Okay, thanks. Thank you very much.